Hello and welcome to the Explaining Rust Analyzer lecture series, where we try to understand how Rust Analyzer works one subsystem at a time. Last time we looked at the base database crate, the crate which defines the input to the Rust Analyzer, the crate which defines the ground truth, the data Rust Analyzer used to derive all various properties of your code, like what colors should be applied for syntax highlighting. At this point, you might be wondering, why are we even discussing all this stuff? Like in theory, Rust Analyzer videos should explain how to build IDEs, how to build compilers. However, what we've been doing so far was mostly discussing state, concurrency, and those kind of issues. The reason for that is that it's really important to understand the overall flow of data through your system. And it is like a really big difference between compiler and an IDE, that in a compiler, you just run the stuff at a single point in time and you work with a static snapshot in the code. Where in an IDE, you really need to care about this state of the world evolving over time. But luckily for you, last time was the last day when we've discussed the overall flow of data for Rust Analyzer. I guess we will be returning there sometime in the future to cover more fine-grained bits, like how do we do configuration management, how do we project reloading. But today we will finally start digging into the compiler. And now we will be exploring Rust Analyzer bottom up, starting from lexical analysis, syntactical analysis, name resolution, type inference, until we cover the whole of the compiler, and then we will probably switch to an IDE. And today is the first video in a series about syntax and parsing. I would expect that it would take me quite some time to cover all of this, so let's get started. Let's go to the Rust Analyzer directory, update the branch, and open the code. Okay, so syntax is covered by many crates, and we will look through them in more details later. But today we will get just the overview of the problem we are trying to solve. Basically, today we will look at the interface we have, and then we will study how this interface is implemented. But to give you just a rough idea, so the parser is the crate which contains the actual grammar of Rust and the handwritten recursive descent parser. The syntax crate is the crate which we'll be looking at, and this is the crate which defines the API for the syntax trees. The implementation of the syntax trees lives in this separate repository, Rust Analyzer Rowan, and we will be looking at it in the details next time, I hope. Okay, so let's go to the syntax lib.rs. And here we have this very nice test called API walkthrough. This test isn't really a test. It's just a extended documentation comment explaining how syntax in Rust Analyzer works. And today we will basically just work this test line by line, discussing stuff. But first of all, let me give an overview of why syntax is important for Rust Analyzer. In general, I would say that syntax analysis, and in particular the data structures you use for syntax tree, is the biggest difference between a traditional compiler and an IDE. If you look at something like type inference, the code in Rust and the code in Rust Analyzer would be pretty similar. However, if you're looking at a parser, then the stuff feels really different. And that's interesting. If you take some standard textbook about building compilers like the Dragon Book or the Modern Compiler Construction or something like that. I don't remember its name. The common thing is that syntax analysis is treated like a solved problem. You just throw lex and yak at it, and you are basically done. Probably have to just like fight off the dungeon elves problem and a couple of reproduced conflicts, and then the interesting part of the compilation starts. You have like intermediate representation, optimizations, control flow graph, and lots of stuff. The story is completely different in IDEs. Syntax tree and working with syntax is actually a significant chunk of what an IDE does, and it's not like we have a really great understanding how we should do this. I guess today's systems like Rust Analyzer and Droslin kind of like converged to a similar design of a front end, but I don't think it actually covered in like any textbook. So let's take a look at it. First, I want to show you one like general IDE specific problem we have. Let's imagine traditional compiler pipeline. Traditionally, compilers are built as a series of transformations from one data type into another. So you start with text, and then you get a list of tokens. And then you get an abstract syntax tree. Then you run a series of desugaring, expressing some of the ISD constructs into simpler forms. So we get simplified ISD, and then you run name resolution and type inference. I guess let's put it that way. So here is like lexing, and here is parsing. Here would be desugaring. Then we have name resolution and type inference, and we get annotated ISD, an ISD where each node has a type. And then we will get into some kind of, so that is like lowering. We get into some kind of intermediate representation, like control flow graph or SSA or whatnot. And then it's like basically backend, or rather LLVM, as all modern compilers basically converge to just using LLVM as backend. Anyway, so what's interesting about this pipeline in traditional compilers is that it is one way. So by the time you get to a simplified ISD, you actually don't care at all about original text. And in fact, what most compilers suggest is that you just track spans across this transformation. So here in a simplified ISD, we only have spans of the original text, but we don't remember which tokens the simplified ISD was produced from, or which ISD it was desugared from. It's only necessary to remember positions in the original text. And why is that? Well, because the only thing you need to do here is to emit debug info and to emit diagnostics and errors, like type mismatches or stuff like that. And for those things, spans are enough. The taxonomy IDE is different. So let's say you have like some struct which has a couple of fields. And then you have function, let's just call it make s, which returns an instance of s, and it is written like this. So the problem here is that we have a type mismatch of sorts. We have a semantic error that we should be passing y here, but we are not passing here. And we are detecting this error at this stage. But what we want to do next is that we want to suggest a fix. We want to have this light bulb field struct fields helper, which inserts y for us. And you notice that the fix is applied on this level. So while these transformations are one way for a compiler, and that works, for an IDE, we actually need to be able to go the other way around and go from here. Actually, using Vim would be more convenient, and go from some internal representation back into the syntax trees. And that's kind of like the main intention you have when you're coding an IDE. When you do some kind of a transformation, you always need to have in mind the reverse transformation. How would you go from lowered representation to original syntax tree? Because when you want to change the original source code based on information you gathered somewhere in the middle of the compiler pipeline, you need to express that knowledge in terms of the original source. So yeah, syntax trees are quite important. What makes syntax trees in the IDE interesting as well is that you need to be able to deal with incomplete code. So when you type something like this, you start typing left, right. Notice that at this point, you, for example, don't have function body. So this is an incomplete function. But still, you should understand that it is a function because you might want to provide some additional help here. For example, one thing Rust Analyzer has, it has completion for parameters. So if you have some function foo and it has some argument, when you write another function, Rust Analyzer will suggest you using the argument of the same name and the same type like the one you've already used in this file. And to provide this kind of suggestions, we actually need to realize by this point that this is actually a function and this is an argument list. So Parson needs to be resilient to the incomplete source code and errors. The second thing which is different is that when you write IDE features, you care a lot about white space and comments. So, for example, if I invoke fill struct fields like this, I get this code. But if, for example, what I've started had different white space like this, the result is different because like IDE also automatically inserts this trailing comma because that's like the code style. You have to add trailing commas at the end of the lines. And to understand the difference between the first case where we don't need comma and the last case where we do need one, we need access to the white space between the tokens. So it's not for compiler, like this trailing commas, this white space is information you want and should and can erase because it's just distracting you from compiling the code correctly. For an IDE, it is crucial because we want to provide automatic source code transformations which look as if they were written by a human, or actually better written by a human. We want to consistently enforce this code style even if the project itself doesn't follow it, because following code style by hand is tedious, and it's much better when IDE does it for you. And it's not like only about formatting. For example, Rust Analyzer has this auto importing infrastructure, and auto importing infrastructure okay, that was actually a bad example where auto importing infrastructure didn't it's like, okay, so what I wanted to show you is that, for example, when Rust Analyzer does auto imports, it tries to insert the import node like in the arbitrary place, which makes the code semantically correct, but also to fit with the overall style, so that if a project does this nesting, then the nesting is respected. On the other hand, if a project prefers flat imports, then Rust Analyzer does like flat imports. And for example, if a project does the grouping into standard library, external crates, your crates, Rust Analyzer tries to honor that. This didn't work in this case because this is actually a re-export, and re-export, although it looks syntactically pretty closely to a usual import, it has very different semantics, so it would be wrong for Rust Analyzer to just add a re-export. So it's correctly added the new import here to the block of imports from external crates, which are not re-exports. So it's kind of like done the right thing, but not the most obvious thing. Anyway, basically what I'm works about is that just like you really want to care about specific source code which is written by the user, but you need to care about all the semicolons, all the white space, all the comments, and that's important. So let's look at the actual API here finally. Again, the goal here is to explain what you have in Rust Analyzer, not how it works. The how it works will be handled separately. First of all, we will be looking at the syntax for this simple function. And to make it easier, let's actually move this function here and run this show syntax tree command. So notice that I have a selection here. So when I run this command, I get internal representation of a syntax tree for the selection. If there isn't selection, I will get a syntax tree for the whole file. And this is a serialization of a structure which we will be looking at in this method. You can see that it roughly corresponds to, well, it's not roughly corresponds, it exactly corresponds to what we have here. What we have here is a function. So the top level node is a function. Inside the function, we have an fn keyword, a white space, function name, which is foo. Then we have parameter list, which is empty. I wonder. There was some feature somewhere where we're, for automatic synchronization of selection between file and what is displayed here, and I'm not sure if it actually is implemented. Anyway, so we have parameter list, and then we have white space after that, and then we have block expression inside curly braces. The block expression is indented. Inside this expression, we have a binary expression, which is a binary addition expression. And it has two operands, both of which are literals. So yeah, pretty simple. Note that the thing on the left is the name of the type of a node. So it's a function, it's a keyword, it is a name, etc., etc. The thing after the @ symbol is the text range of a node in the document. And this text range is in terms of absolute positions. So that means that like symbols from 7,000 something to 7,000 something is fn. And you note that, the difference here is just 2 because keyword is 2 bytes long. And finally, for tokens, not for internal nodes, we also have the string representation on the right to make it easier to understand what this talks about. Okay, so with this in mind, let's look at the API. First, we call the parse method of the source file. Source file is one of the syntax nodes. And actually, if we show syntax tree for the whole file, then we see that that's the root node. Okay. What it returns is a parse. notice that a parse contains two bits of information. It contains the parsed IST node, and it also contains the list of errors. Why do you not understand? What? How? Oh, okay. Yeah, that's okay. That's a feature I was talking about. So when you have this IST opened, you can apparently press go to definition, yes, and get the position of this thing in the IST. I actually haven't ever used this feature, so I don't even know if it works or not, but apparently it works. So cool. Okay, yeah, they disabled this. So yes, parse contains a list of an errors and also the tree. In a sense, while in like traditional compilers, a parse function will look like this. It will return a result with either an IST or a syntax error. In Rust Analyzer, we never ever want to fail parsing. We want to parse arbitrary things. So our parse function signature is actually more like this. We always return an IST. And alongside with this IST, we return a list of syntax errors. One important thing to note here is that IST here exactly corresponds to the source code. So traditional compilers during parsing also often do IST repair. They try to guess what the user have meant to write, and they try to surgically change the IST in place. So for example, if you are missing a semicolon, then the IST would actually have a semicolon, but there would also be an error about semicolon missing. And that is to make further steps of the compiler pipeline more reliable. In an IDE, we cannot do this. If there isn't a semicolon, we need to understand this fact, and all the further transformations need to be aware that the semicolon is missing, and we need to have a fix to add this semicolon. So we don't do this. The IST is a lossless representation of the text. So we won't be looking at the syntax errors, and truth to be said, the design of syntax errors is basically undone. We like emit some kind of syntax error, so this error is from Rust Analyzer, but like we've paid zero attention to it, and the design is probably wrong. What's interesting here, though, is that I think when you're writing command line compiler, providing high quality syntax errors is really important because it helps you to explain what's wrong and how to change the code. However, when you're writing an IDE, you don't really need high quality syntax errors. Like they won't harm, of course, and they will be better, but there's a killer feature which to a large extent alleviates the need to have precise syntax errors. And it is the fact that you get immediate feedback when you type stuff in. So you see that any incomplete thing is like immediately underlined. And as soon as I type something correctly, then the error goes away. This ability to get instant feedback about correctness of the code allows a different workflow. You basically just type things and you see when they are correct. You don't even have to waste time to look at what the error message is saying. You can just try various fixes and see what works, and you're done. Okay. So finally, we've extracted this source file, and let me actually restore this back. We extracted the source file, and again, source file is a specific IST node corresponding to the root of a file. It's not just like some abstract file. And this IST node has a well-typed API. For example, there is this items method, which return a list of IST item. And we can iterate children and extract the first item, which is a function. And in this case, there is only one item at all, the function, because the file we are parsing contains only this function. So yeah, we extract this function. Similarly, function again is an IST node and it has well-typed accessors. So when we ask for a name of a function, we get back an IST name. Important thing to note here is that although function names in Rust are mandatory, the IST method function returns an option here. And that is because syntax trees are built around incomplete code. So we never make an assumption that an IST node, which is required by the grammar, is actually present in the source code. This is reflected in types. And all further code which will use function name will have to deal with the possibility of the absence of the name somehow. So we don't do repair, we just make sure that all the consumers of the API work with incomplete syntax trees correctly. But in this case, we know that the name is not none, so we can unwrap it, and we can compare that the text of the name is actually full. Then we continue drilling down this function body, so func is this thing, and then we get for function body, that would be this thing. It would be a block expression. And block expression contains statements and then a tail expression. So we can extract this tail expression, which is binary expression. So let me illustrate this better. So we can have something like this. And if we take a look here, we see that block expression contains a let statement, which ends with this semicolon. Which ends with this semicolon. And then it contains expression statement, which ends with this semicolon. And finally, it contains an expression, which is not an expression statement. That is the tail expression, which will become the value of this block. So this actually isn't type correct code, and we need something like this. And actually, I need to stop typing this myself every time because we have this feature to automatically fill up the return type. That's also interesting that although I use Rust Analyzer, by this time it has so many features that I don't myself consciously remember all of them. And sometimes I do some things by hand, which actually the IDE can provide for me. And this goes to one interesting design challenge when building IDEs, is that the hardest thing is actually telling the user that this feature exists. And in this particular case, the way we should signal that this feature exists is by emitting an error in this position. That will allow the user to understand that, hey, if this is an error, it might have a quick fix. So the user invokes this. The reason why we don't emit a diagnostics here, a warning here, isn't really great. Basically, historically, we avoided emitting many warnings because Rust Analyzer was incomplete and had many false positives. But today, we more or less completed all of our macro expansion and name resolution and type inference systems. So we should be able to produce these warnings correctly. And again, someone should send a pull request graduating this assist to a diagnostics. In terms of code, it would be something like return type. Yeah, so currently this feature lives in this assist. And we probably want to move it into IDE diagnostics crate, so to this thing. Anyway, this is going beyond the scope of today's lecture. Let's go back to where we are. Yeah, so we've extracted a binary expression. And by the way, all those IST things implement display. So you can do something like this. And again, this is again the case where I do manually something which an IDE does for me. I should have done this instead to autofill the println. Yep, so these things are display. And if you display them, you get back string representation of an IST. And the invariant here is that the string you get back is exactly the same string which were used to produce the IST in the first place. That's like one-to-one correspondence. IST exactly corresponds to the original source string. Okay, so we get an expression. An expression is an enum of all various kinds of expressions, so we can match on this expression to downcast this to a binary expression. And note that all IST in rationalizer are, all enums in rationalizer IST are one level deep, so it's not like binary expression of a left-hand side operator and right-hand side. It's always just like single expression, and then you get various accessor methods on this result. And that is because, again, left-hand side and right-hand side might be missing, so they need to be optional, and if stuff is optional, then deep pattern matching isn't really that useful. Okay, so that's in a nutshell how the IST API works. What's interesting though is that an IST, which gives you typed access to the nodes, is actually a thin layer on the CST. And to get a concrete syntax tree out of IST, you call the syntax method. And what you get back is a syntax node. And the syntax node is the same for all various kinds of IST nodes. It was called func. So yes, this one is an IST expression. This one is an IST FN. But their underlying syntax is the node of the same type. So this means that rationalizer has general infrastructure for traversal of the underlying untyped syntax tree. Yes, and the way IST works is that let's go back to our original source code, show syntax tree. What you see on the right here is actually the syntax node layer, the concrete syntax tree layer. And the way ISTs are implemented is very simple. Each IST node, it's just a wrapper around untyped syntax node. There is no additional data there. And what such an IST node is, it's just an invariant, a constraint that this particular untyped syntax node indeed holds a value of this specific type, like of specific binary expression. So you see that we don't have a two-layer node here. We don't have an expression whose child is a binary expression. We just have a binary expression node. And that means that the syntax of this expression node and the syntax of a more strongly typed binary expression node is the same. So that means you can look at the same syntax node using various granularity of types. In particular, you can look at expressions as, well, arbitrary expression, which is enum of every possible expression, but you also can look at it as a specific expression. When you want to go in the opposite direction, from an untyped node to a typed node, you generally call the cast method. The cast method just checks that the syntax node is indeed of a type you want to cast to. It fails, it might fail, so it returns an option. Here we take an expression, then go to its syntax here, and then cast back to expression, and that works. Finally, so not finally, like pause. So one thing you need to understand here is that as abstract syntax tree is just a wrapper on top of syntax nodes, on top of untyped syntax tree, that means that all the actual data is stored in syntax nodes. And now we will look at the actual data here. So first, and we sort of actually seen this already here. First, each syntax node stores a kind. Kind is a fieldless C-style enum which lists all the various syntactical elements of Rust, both tokens and internal nodes. And let's see how many of those we have. So line 7 is the start, and line 259 is the end. So there is about 250 syntactical elements in the Rust language today. Okay, so that's the kind. The next thing the syntax node stores is the text range, which is the range in the original file of the text of a node. We used a new type for representing text ranges, which comes from the text size crate. It's really simple. It contains two types: text size, which is a new type around U32, and text range, which wraps two text sizes with an invariant that the range is well formed, but it is allowed to be empty. Okay. The next thing that syntax node has is the text. You can go to screen by using display. But you can also call text method, which returns syntax text. The difference between the two is that syntax text actually is just yet another view into the tree. The actual text is stored only in the tokens. So when you want to get the text of the internal node, you need to walk the tree and collect the text of all the tokens. This syntax text type provides that functionality without actually building a single in-memory tree. So when you compare with something, it walks the string dynamically, while toString will do an allocation and return you a bona fide string. Okay, finally, let's go to the traversal methods. I guess we will cover the bulk of them in a separate lecture, but now just to get a basic understanding. The parent returns parent syntax node. And as the parent might be none, this returns an option. There are two methods for accessing children. Actually, yeah. One thing I didn't say is that we do make distinction between tokens and interior nodes. So there is syntax node, there is syntax token, which is a leaf node, and there is node token, which represents either of those. When you're working with syntax nodes, you can ask first child, and generally when we speak about children, we speak only about node children, not token children. So if you go back to the original example, this one, and you ask function children, what you would get is a name, parameter list, and block expression. You wouldn't get white space or function keyword. If you, however, and that's like children method, if you, however, ask for children with tokens, then you get all of those. And the motivation here is that most of the time you only care about non-token children of the node. Okay. So first child token. It returns the first child token of this node. We look at its kind, and for our body, it would be the opening curly brace. The capital T macro takes a string representation of a token and returns a syntax kind for this token. This is out-generated code, so it is pretty horrible if we do. I wish Rust T was able to format it, but it doesn't do this, so let's just manually look at first element. Okay, so this means that if we type tbank semicolon, what we have back is the semicolon syntax kind, this thing. It's basically the more convenient way to represent tokens, and this is 100% stolen from the sync crate. So thanks, David, for inventing this kind of API. It's like really helpful. Okay. We can also get to the siblings. So when you are a node in the syntax tree, you have a parent, you have children, which are direct children, you have siblings, which are neighboring nodes. You also have ancestors, which are parents of the higher rank, like parents of parents, and you also have descendants, the children of children, etc. Both descendants and ancestors in Rust Analyzer are closed. So if you ask for ancestors, you also get the node itself. Also, if you do something like expert siblings, I think you also get the node itself as well. So everything is closed. And yeah, for example, here we assert that if we look at the expression, the 1 plus 1, and look at its siblings, then at least one of those siblings will have a kind of curly brace. And we also can count all of the descendants of the node. Note that like descendants is generally like the single bad method in terms of complexity, because looking at the direct children, at the siblings, at the parents, usually returns a small amount of nodes. However, the amount of descendants can be pretty big, because syntax trees are generally wide and shallow. Finally, there is this very generic method for traversing nodes called preorder, where you can walk the nodes and do something when you enter node token or when you exit node token. And this code, for example, produces an indented representation of a syntax tree. This is similar to the code which produces syntax trees like this. So basically, this is implemented in terms of this, and we will look at this later. Okay, so this iterator methods for accessing neighboring nodes play really well with the cast methods, because you can take an iterator and then filter map, or maybe find map something using a cast, and then you will find the corresponding node of a specific tree. So here we collected all the expressions in the node. The other way we can do it is by using merge AST syntax. What it does, it's like a proc macro. Well, it's not a proc macro, I think. Is it? Match AST. No, it's usual macro by example. Yeah, it's usual macro by example, which abstracts over a series of casts and gives you a nice match-like syntax where you can say like AST expression is this, and like AST statement is that. So yeah, I guess that covers most of it. Please take a look at this test yourself and study it in more details. But in a nutshell, Rust Analyzer has API for accessing syntax. There are several like core tenets of this API. The very first tenet is that the API is lossless and resilient to errors. When you parse something, you cannot get an error back. You always get some kind of a syntax tree. And this syntax tree losslessly represents the underlying text. The second tenet, which I haven't talked about, but which is pretty important, is that syntax trees are values. In many traditional compilers, it is customary to attach various auxiliary bits of information to a syntax tree, like types, name resolution results, whatnot. In Rust Analyzer, all this information is stored elsewhere in a source database, and syntax tree is just the data. In some sense, the string, which represents the syntax tree, and the syntax tree itself store exact equivalent amount of information. You can always go from syntax tree to the string by calling toString, and you can always go in the opposite direction by calling parse. Finally, well, not finally. Another peculiarity of the syntax trees API: everything is optional. Even if the thing is required by the grammar, the actual accessor will return an option to you, because we need to account for cases where the syntax wasn't fully typed out by the user. But if you get an option, you can be sure that when we parsed this file, we actually emitted the proper error there, so you shouldn't care about needing to report this one more time. Finally, the IST is actually two-layered. The underlying layer, what we will be studying next time, is the so-called syntax tree layer. It is an untyped tree of nodes. Each node in this tree has a kind, which is just a fieldless enum, a text range, and a list of children. These untyped nodes also provide traversing API. From a specific node in a tree, you can also go to a parent or to any siblings or to descendants. And on top of this untyped API, we add the IST layer, which is pretty simple. Each IST node wraps a single syntax node, and the only thing it does is that it enforces that the underlying kind of a syntax node actually corresponds to the static type of an IST node. Yeah, and one more detail, which is related to the code style in Rust Analyzer. When we use types from the IST, we always prefix them with IST : We never import that directly. And that is because we have many different instances of the same concept. Like we have like 3 structs here. So it's important to, when you're talking about a struct, it's important to understand at a glance. Are you talking about IST struct or here struct or item tree struct or something like that? Okay, I guess that's it for now. And next time we will look at how we will actually implement this magical lossless and error resilient syntax node layer. Thank you for listening. Bye.